Okay, here we're trying to make a video to talk about electromagnets, specifically the effect that if you have a current carrying wire, then it will create a magnetic field. Let's just pretend our current, we remember that that has the symbol I from the last unit, and it's going in this direction. Then what that means is that above the wire, the current would be going, the magnetic field, it would create a magnetic field going in that direction, and under the wire it would create a magnetic field going in this direction. So this would be above, and this is below. Let's try and make that a little bit clearer. See, it's sort of going behind it there. Now, what's tricky, I'm trying to draw three-dimensional things in two dimensions, so we're gonna struggle with this a lot. But it's not really that critical what direction the magnetic field is, so much as to recognize that the current carrying wire has created this magnetic field. It just naturally starts happening when the current passes through the wire. The guy who discovered this is Ørsted, but I find that a little bit odd because I think this discovery is often associated with Ampere, but it doesn't. I guess that doesn't really matter. Anyways, above what he actually did was he took a current carrying wire and he put a little magnet next to it, like this. So let's just say that this magnet is hanging on a string that is sitting above. And what he discovered was that that magnetic field always turned in the same direction, so it turned like that. So the force that caused that magnet to turn is the magnetic field, or some magnetism that's created by that current carrying wire. To determine what direction something is going, or what direction the magnetic field will be going, we'll use something called the right-hand rule, and we'll get lots of practice with this in class, but essentially the right-hand rule says that if you put your thumb in the direction of the current, and then you close your hand, and sort of do this by closing your hand a little bit, like let's say you're imagining yourself holding on to the wire itself or a broomstick or something like that, and then the way your fingers wrap around will show the direction of the magnetic field. Here I'm going to try and draw this. I've had to re-record this video because of this already once. And here's the palm of your hand, and you can imagine your fingers would be wrapping like that. Okay? And here's the wire moving through your hand. And then your thumb is in the direction of the current. And what you can see is behind the wire, or underneath the wire, your fingers are wrapping in one direction and above they're wrapping in the other. And that shows the direction that this magnetic field is going on. Above the wire it's going from left to right, and below the wire it's going from right to left. There's a special convention to help with drawing things in three-dimension. That convention suggests that if you're coming out of the page, you can imagine that that's like the tip of an arrow, and you're in the wrong spot because that arrow is flying towards you, so that's coming out of the page. And if you're going into the arrow, or going into the page, then you can see the back side of the arrow, and those little feathers, or whatever you call them on the back side of the arrow, are called the fletching. So you see the fletching of the arrow. But essentially what that means is that's the symbol for into the page. So we can just play around with the right-hand rule here. This is something you need to practice, and you will get the hang of eventually. Probably something easier to show in not in a video but in real person. But we can try and practice with it here anyways. So let's just say that we have that symbol right there, and that is showing us the direction of the current. So if you imagine then, if you're watching this on a computer, you can try and put your thumb straight into the computer screen and then wrap your fingers. And what you should see is that your fingers are pointing down on this side, up on this side, left to right on that side, and right to left on this side. And so if we imagine the magnetic field that is spiraling around that wire, it would be spiraling in that direction. What that means then is if you took a magnet and you hung it right here, that the north end of the magnet would go down and the south end of the magnet would come up. Alternatively, here we have the symbol Remember, this means into page. Here we have the symbol for out. So what that means is the current, you can imagine, is shooting straight out of the monitor and right into your eyes. Very exciting. And if you put your thumb in the direction of that current and then you wrap your fingers around, I think you'll see that the current, or your fingers in this case, are going down here, up here, and over here. Yeah, that's right. And like that. And what that means, for example, is if you took a magnet right here, north end would want to point that way and the south end would want to point that way. Because if you haven't watched the last video yet, what we know is that the direction of a magnetic field gives the direction a magnet would want to point. So there's just a couple practice. Again, though, I think what's more important about this is not that we can predict the direction that the magnetic field will happen, is that we recognize that any current-carrying wire will produce a magnetic field. We can observe that magnetic field by seeing how it interacts with other magnets, and that there is some strange convention for figuring out what direction it's going. Now, you can imagine that if we could simply create a magnetic field by using a wire, that would be great, and we can. But the problem with it is that those magnetic fields tend to be very small. So what we want to do is we want to create a geometry with the wire that's going to create a magnetic field that is a little bit stronger. If we imagine taking a wire and wrapping it into a coil, the way I've drawn this coil is that if this was your pencil, okay? Actually, I'm going to try that all over again. Hold on a second here. Let's say you have a pencil. Let's start with the pencil. There's your pencil. Okay. There's your eraser. That's nice. Okay. You're going to take your wire and you're going to wrap it so that it hits the front, comes across the front, and then it comes out the back and wraps across the front, and then comes out the back and wraps across the front again, and then comes out the back and wraps across the front. Oh, that's a little unclear. I'll try that one again. Out the back and across the front, and eventually comes out the back and back to, oh, excuse me, back to some sort of battery. Like that. Okay. Then what we're going to see is that on the right-hand side of the battery, so I'm going to start here, or the battery, the pencil, we've got wires that are consistently going into the page. Alternatively, on the other side of the let's do this in red. The other side of the pencil, we're going to have wires that are consistently coming out of the page. What that's going to mean, let's use the right-hand rule for the. We're gonna start with the side that we drew second. Here, you're putting your thumb straight out of the monitor, and then you're going to see inside the coil that that's creating a magnetic field that is going up. Again, you take your right hand, make sure it's your right hand, put your thumb so it's coming straight out of the screen towards you, and then let your fingers sit inside that coil. And what you're going to see is if your thumb's in the right spot, it's pointing up towards you, that your fingers are pointing up towards the ceiling. Alternatively, let's go over to the right-hand side of the coil now. So now we're over here. Okay? We're going to put our thumbs, that's the symbol for in. We're going to put our thumbs right into the monitor. We're going to curl our wrists all the way around until our fingers are inside that coil. And what we're going to see is that the magnetic field associated with that is going up. So a magnet placed in there would come up to this end, so would point to this way. So what that means is you call this the north end of the magnet, and this is the south end of the magnet. So that shows us why creating a coil, or creating what they call the fancy name for a coil in magnetism is a solenoid, can create a very strong magnetic field. Because you notice here on the right you'll have 1, 2, 3 things working together to create a magnetic field, and here on the left you'll have 4, 5, 6, and all of those magnetic fields are pointed in the same direction. And so 1 plus 2 plus 3 plus 4 plus 5 plus 6 will all work together to make a strong magnetic field. So this is why whenever you're studying magnetism or looking at magnetism, you're seeing all these coil shapes, because by creating the geometry of the coil, we create a situation where all of the currents are working to create magnetic fields, at least within the coil, that are all pointed in the same direction. All those coils, all those magnetic fields will add to make a very strong magnetic field. Just a little side note, I don't know when else to mention this. If you put a piece of iron or something in the middle of the magnet, inside the coil, then, as discussed in the last video, those domains inside the coil will all try to line up with the magnetic field that's being created, and when that happens, we will create a stronger magnetic field. So if there's iron inside the coil, that's going to make the magnet much stronger. So that's why, for example, when you see something like an electromagnet in a crane, the magnet's almost always going to be circular. What you're seeing there is the circular piece of iron that's sitting inside the coil that's creating the very strong magnetic field. And so the coil geometry allows the magnetic field created by the wire, the current in each individual wire, to add so that they're all going the same direction, and then the iron serves to, for lack of a better way of putting it, amplify the magnetic field created. Right-hand rule for solenoids. You don't actually need this. You can use the old right-hand rule if you're feeling very comfortable with it. But if you go back up to that solenoid that we had up here, I'm just going to redraw him down here so we can work with him again. There's our left-hand side. Here's our right-hand side. Then there is a simplified way of determining the magnetic field inside that coil. If we put our fingers in on the right and up on the left. So you can see we have all the in symbols on the, I should stick with my color coding. We have all our in symbols on the right and all our out symbols on the left. So you can play along here. Line up your fingers with the black right-hand side ins so that they're pointing straight into the monitor, and then curl your hand so that in front of the ins you see your fingers still pointed in, but in front of the outs they are now coming out of the monitor. Then your thumb direction is pointing straight up, okay, and that gives you the direction of the magnetic field. So that's the secondary way to do it. We can try that again, but let's reverse our coil this time. Let's just pretend we hooked up the battery in completely the opposite way, or we wrapped the coil in the opposite way in the first place. Then what we're going to get is we'll get all ins on the left-hand side here and outs on the right-hand side. And now we're going to put our fingers in front of the left-hand side and then curl them so that they're coming out on the right-hand side. And there's no other way to do it. Your thumb must at this point be pointing down, making the north of the coil and the south of the coil. So that is an alternative right-hand rule for solenoids. But as you can see, that right-hand rule, if we compare this diagram and the diagram we created with our original right-hand rule right here, are consistent with each other, and so there's no need to learn the secondary right-hand rule if you understand the first right-hand rule. That's really up to you. That's enough for how well, let's just go through the quick review again. I think that's worthwhile. So if you have a current passing through the wire, it's going to create a magnetic field. There's some relationship between electricity and magnetism. We don't totally understand it yet, but we're just starting to look into it. We can tell because if we take a magnet and we put it near a current carrying wire, it's always going to turn in the same direction. We made up a convention for drawing things in and out of the page. Remember the arrow, so the tip of the arrow pointed towards you is coming out at you. The fletching or the feathers on the back of the arrow going in is pointed towards you. And then we used it to create a useful geometry in a coil that helps us make multiple current carrying wires make magnetic fields in the same direction to make them stronger. And then we just learned the secondary right-hand rule that shows an easier way for coils to determine the direction of the magnetic field.